Hello all, thank you for coming. This is me, Adel Bibi, and this is a joint work with Matthias Mueller, supervised by Dr. Bernard Ghanem from KAUST. The paper title is Target Response Adaptation for Correlation Filter Tracking. So we'll start by introducing to you what a visual object tracker is. It is basically the process of estimating the state of a bounding box that covers an object of interest in consecutive frames under a variety of challenges like occlusion, fast motion, motion blur, and etc. So because we are mainly interested in correlation trackers, so here is a brief insight on how they work. Basically, what we wish to do is basically to solve the rigid regression problem, the standard problem, where we wish to try to find the filter W that once correlated with the templates in the rows of the matrix X regresses to a target Y having a minimum energy. So however, for computational purposes, what people do is they set the data matrix X as a circulant matrix, where under the right homogeneity conditions, this would mimic, the circular translation would mimic an actual translation in an image. So to solve this problem, we could either do it in the primal domain or the dual domain. If we wish to solve it in the primal domain, we can solve it for multiple templates, where X here is blockwise circulant matrix. However, if we solve it in the dual domain, we can use the kernel trick, since we can write it as a pi product format of this data matrix. So basically, the question is, how would people set the target response Y? The answer is simply using a Gaussian pulse centered around the previous location. The reason behind this is basically simplicity, the assumption that the object does not move significantly between consecutive frames, and to reduce the effects of circular boundary conditions. So here we show the motivation behind our work. Standard correlation trackers will fail under partial occlusion and fast-moving objects. For instance, image patches here, B and C, are generated from the previous image patch in A under actual translation and the proxy circulant translation from the same image. As we can see, patch C applying a circular shift to the object while it's under an occlusion would cause both the target and the occluder to move simultaneously in the image, and this would damage the tracking performance. More clearly in the fast motion category, as well as in image patches E and F, which are generated from the image patch D under the actual translation and the proxy circulant translation. Again, the circulant shifts for the target is completely different than what we'd have in the image, and again, damages the tracking performance. And here, basically, what we want to do is to test the hypothesis of how important is this designing this target response. And what we do basically is we pick 5 different correlation trackers that all use this Gaussian pulse in the center. So on your left-hand side, what we did is basically we have reinitialized the center of this Gaussian from the ground truth. And as we can see in the dashed line, the improvement is significant, almost saturating the OTB 100 data set. And another experiment to see how sensitive it is what we did simply is we took this Gaussian pulse and perturbed it by at most randomly 2 pixels in every iteration, and the tracking performance drops significantly. So the question here is, can we do better than a Gaussian pulse? So the proposed pipeline goes as follows. So in the left column is the standard correlation trackers, while the one in the right is our framework. So basically in our framework, what we do is we replace this Y with an observation Y0 that holds an exact translation detections from the image. Unlike before, where even if we had an incorrect detection, the tracker can still recover as it is trained over Y0. In our framework, Y0 can be interpreted as a prior knowledge on the motion model. Now, in practice, in ideal scenario, we wish to sample all possible translations of the image. However, this defies the purpose of using circulant property, and thus we stick to interpolating the samples that we collect. Therefore, what we do is we add the following regularizer, and we solve for both the filter and the target response Y. And to make things more interesting, what we do is we replace the block circulant matrix, the circulant matrix with a block circulant matrix, and solve it in the dual domain to make use of the dual equivalence. And the solution is, by using the inverse lemma there, is given as follows. It is not only nice because it's element-wise operations, however, because the final solution is written as a sum of all multiple templates together. And we can also use the kernel trick again, because now we have managed to solve 3 problems at the same time using kernels, multi-templates, and solving the issue of the target response. So basically, we have tested our framework on 5 different baseline correlation trackers, only to improve all of them, specifically on the fast motion, motion blur categories. In the trackers in blue are the baseline trackers, where the ones in red is our framework adapted to it. So as we can see, our framework improves the tracker significantly on the corresponding attributes. So, of course, we don't stick to the quantitative results, qualitative results. We have also quantitative results where we show that all the trackers, correlation trackers that we have tried improve significantly, ranging by a factor of 4 to 15%, some of which also achieve the state-of-the-art performance at the time of submission. The improvement is also shown for the corresponding attributes as well. Thank you all for coming. This might not have been a very deep talk, but we'll be very pleased to have your questions at the poster 5. Thank you very much.